Hello. In our last video we discussed a simple solution to the Schrödinger equation involving a model called the free particle. In this video we'll look at another very simple model called the particle in a one-dimensional box. The basic model for the particle in a one-dimensional box involves a potential field where the potential is infinite outside of the box, so it acts as a barrier preventing the particle from getting outside the box, so the box remains trapped. Inside the box, the potential energy is zero. So the only difference between this and the free particle is the infinite potential outside of this area called a one-dimensional box. In the case of the free particle, the potential energy, you'll recall, was zero everywhere. So what we want to do is determine from the Schrödinger equation the wave function for this system and the energy corresponding to this particular very simple model. Now here's a diagram which shows the basic idea. We have the barriers indicated here and here, where we have a discontinuity in the potential energy. Outside the barriers, we'll find the potential energy is infinite, and inside the potential energy is equal to zero. Now we've already mentioned that because we have an infinite potential, the particle remains trapped in this region between 0 and A. We'll prove that mathematically in a second, but because the particle remains trapped, if we remember our basic definition of the wave function, if the particle cannot exist outside the box, then the wave function must be zero outside the box. That's very important. Remember, the wave function is related to probability. If there's zero probability of finding it, the wave function is equal to zero. So our quest is going to be to determine the wave function inside the box between the barriers labeled at position 0 and position A. Okay, well let's just take a look real quickly at how the Schrödinger equation shows that the wave function has to be zero outside the box, even though it should be intuitive to you that if the potential is infinite, it's like having an infinitely high wall. You can't get over that wall, so there's zero probability, so our wave function should be equal to zero. But this is relatively simple, so let's just go through it. Here's our Schrödinger equation, which shows the wave function psi, and the total energy E, and the potential energy is equal to infinity. Now, if we simply rearrange that equation to solve for our wave function, then we have this expression that you see here. And let's look at the first term. It's 1 over infinity minus E. Well, 1 over infinity minus E is because infinity is infinity and E is insignificant in comparison. That's the same thing as 1 over infinity. And we know that 1 over infinity is equal to 0. So therefore, since that first quotient is equal to 0, the wave function itself is equal to 0, and if the wave function is equal to 0, the zero probability of finding the particle outside the box. Simple enough, right? Alright, so let's look inside the box and look at the solution to the Schrödinger equation there, where the potential energy is equal to 0. And we end up with an equation. If you do this, go back to the previous video or go back to your text and take a look at it. The Schrödinger equation we have here is the same as what we had for the particle, the free particle in space, because the potential energy is infinite. And therefore you expect the solution to this equation to be the same as that for a free particle. Alright, so again, rearranging the equation here as we did before, where we've just divided through by this quotient. We get this, again, as we mentioned, the same solutions as we had for the free particle. And again, I won't go through this in heavy detail, but we talked about this in the previous video. So here's an expression for the wave function psi. Okay? So what's the big deal? It's the same as a free particle. Well, there is one important thing here, and that is what we have are boundary conditions. And because the particle is bounded, we're going to have to augment our solution to some degree to reflect those boundaries. But before that, we actually have to rewrite our wave function in trigonometric terms. It's going to turn out that it's a whole lot easier if we do this in terms of sines and cosines to solve the problem. So we have something called Euler's formula here, this relationship which allows us to show that an exponential term with an imaginary exponent is equal to the sum of cosine and sine functions. We won't prove that here, but you can find that very readily in a mathematical textbook that shows that e to the ikx is equal to the sum of terms. You'll notice, of course, that the sine term has the imaginary character I, square root of negative 1, in that second term. So we have a complex relationship involving trig functions. This is going to be useful because you remember, of course, that our wave function is equal to e to the plus or minus ikx. So because it's e to the plus or minus ikx, we can rewrite that in terms of cosine and sines. So that we've got this expression here. And again, just remember here that this a that occurs in front of our wave function is a constant. We're not particularly worried about the value of this constant right now. We will talk about this constant or these constants in a future video. But what we're most concerned about, of course, is e to the ikx. And so we see the comparison here with e to the ikx. We can write it as a sum of a cosine and a sine term. You'll notice that in this expression that we've written for psi, there's no imaginary component, but we're going to assume that that's embedded within this constant d here. Again, these are arbitrary constants right now that have no specific value, although we're going to determine what those values are later on. So that I is assumed to be embedded in the function here, so we're not explicitly writing it out. So again, this particular relationship allows us to write the wave function as the sum of a cosine term and a sine term. All right. Now, back to what we talked about earlier with boundary conditions that we have to consider in the case of the particle in the box that we didn't have to consider in the case of a free particle. And those boundary conditions are related to the fact that our wave function must be equal to 0 at the boundaries, because outside the box it's equal to 0. And you must remember that one of the conditions of our wave function is that it's continuous. And because of that continuity, if we take a look here at a simple little diagram that we're drawing for our barrier that shows the region 0 to a, where outside the box the wave function is equal to 0, and so that means at the boundaries it's equal to 0. Because the wave function must be equal to 0, that means that when we figure out the wave function inside the box, it also must be 0 at these boundaries. Okay, and that's very important. So just succinctly mathematically we write that as we have right here. All right, well, let's first consider the boundary where x is equal to 0. Okay, so here's our wave function in terms of our cosine and our sine functions. And what we're going to do is we're just going to very simply look at what happens when that is x is equal to 0. So here we have taken x, set it equal to 0, and plugged it in to the expression. And we'll note, of course, that the cosine of 0 is equal to 1, and the sine of 0 is equal to 0. So that means that the first term then becomes c times 1, and the second term then becomes d times 0, which of course is equal to 0. So that means when psi is equal to 0, that means that the value of psi of 0 is equal to 0. That means that c itself, that coefficient c itself, must be equal to 0. So if the coefficient c is equal to 0, that means we can just simply eliminate that term in our wave function, and we're left with just the sine term for our wave function, so that psi of x is now equal to this coefficient d times the sine of kx. Okay, again, this is important. The boundary conditions require that the coefficient c be equal to 0, so the cosine term disappears from our expression from the wave function, and we're just left with the sine term. Alright, now we're going to look at the position x equals a. Again, psi has to be 0 at this particular position, and so we're going to take x equals a and plug it into our wave function so that we have the wave function being equal to d sine times ka. Alright, so the question then is, under what circumstances do we have psi of a being equal to 0, or d sine ka being equal to 0? Well, we have two possibilities. Either the sine of ka can be equal to 0, or d can be equal to 0. But if d was equal to 0, that means that our wave function would be equal to 0 everywhere, because both coefficients c and d would be equal to 0, and that's an unacceptable solution, because if the wave function is equal to 0 everywhere, that means a particle doesn't exist. A particle has to exist. We've said it exists. So that's an unacceptable solution. So the only possibility then is that the sine of ka is equal to 0. Alright? Well, so under what circumstances will that happen? Well, again, going back to properties of trig function sine, we know that the sine of n times pi, where n is equal to an integer, will be equal to 0. So again, going back, the sine of pi is equal to 0, the sine of 2 pi is equal to 0, the sine of 3 pi is equal to 0, the sine of 4 pi is equal to 0, etc. So if that means that k times a must be equal to n times pi. That's the only way that function is going to be equal to 0. Alright? So, if we know that k times a is equal to n times pi, as long as n is equal to an integer, then we can solve for k and find that that's equal to n pi over a. And then what we can do is just simply, remembering here that we've got our original function is the sine of k times x. Let me just write that here again to remind you of that. And plugging the value of k into that, or the expression for k into that, that then leads us to an overall function here for psi, where it's equal to d, an unknown coefficient at this point, times the sine of n pi x over a. Alright, so there's our wave function. Okay, and again, the requirement is that n be equal to an integer. Alright, so what are the implications then? What about energy? So we have our expression for the wave function psi. We see that the boundary conditions give us a wave function that is different from that of the free particle. What about energy? How does that differ from the free particle? Alright, well, again, going back to what we said earlier on the previous slide, k is equal to n pi over a. We also know from the Schrödinger equation, when we solved it earlier, that k was equal to this expression, which has energy in it. Okay, so if we just simply do a little bit of algebraic rearrangement here and solve for E, okay, then we get this expression here, which again has the integer n is equal to 1, 2, 3, 4, and above. If we recognize that h bar is equal to h over 2 pi, we can simplify it a little bit. Making that substitution eliminates the pi. And so we have n squared h squared over 8ma squared. Again, a would be the length of our box. So here we have energy. Alright, well, what's the big deal here? If you remember the free particle, there were no constraints on energy. In this case, because n is an integer, right, that means that we have a situation where all energies are not possible. This means that we have energy levels because of the fact that n only takes on values of 1, 2, 3, etc. So we can draw this out. For example, when n is equal to 1, the energy is h squared over 8ma squared. When n is equal to 2, we have 4h squared over 8ma squared. When n is equal to 3, we have 9h squared over 8ma squared. So we have these energies as allowed, and of course we can do it for n equal 4, etc. But you'll notice that because n can't be, for example, 1.5, we can't have any values in the regions between the levels. So we have levels, we have quantized energy, we do not have continuous energy, as we did in the case for the free particle. So boundary conditions, the bounds associated with the infinite potential, give us energy levels. That's the only difference between this problem and the particle, the free particle. The boundary conditions, when we have the boundary conditions, when we apply the boundary conditions, we get energy levels. This is a remarkable result from the Schrödinger equation. Remember, this model is very, very simple. It's only one-dimensional space. We only have two possible potential energies, infinite outside the region from 0 to A, 0 inside the region of 0 to A. And when we get that, we get energy levels. And remember, this was one of the great mysteries of atomic spectra. We go back to the Bohr model of the atom. How do we get discrete wavelengths that appear in the spectrum? We assumed energy levels. Bohr assumed energy levels. But he had to make that assumption. In this particular circumstance, we see that energy levels fall right out of the solution to this equation. This is amazing. We get, again, energy levels because we have boundary conditions. And we'll see this repeatedly over and over again as we look at more complex problems. Whenever we have boundary conditions, whenever we have a variation in the potential energy, we will have energy levels. Only certain levels of energy are available to the system, atom, molecule, whatever it may be. We don't have a continuum. We don't have a continuous range of energies whenever we have a variation in the potential energy. This is important to remember. In our next video, we'll continue with discussion of what this means with regard to quantum mechanics and the basic postulates of quantum mechanics before moving on to additional discussions about what the results from these models mean and how they apply to physical systems.